Howdy, we are the Texas A&M University Aggie Solar Team. This is our pitch to present Cheyney University of Pennsylvania with the new photovoltaic and battery storage system for the Hero X Solar District Cup. My name is Connor, along with Dalton, Dylan, Jongsoon, Kyle, Mark, and Dr. Abdulal. We want to give a special thanks to Dr. Abdulal for overseeing the project and the industry professionals who we consulted with. I will now pass on to Dalton to discuss the objectives of this project.
Thank you, Connor. Our team's objectives for this district use case included reducing Cheyney University's consumption of natural gas and electricity by expanding their on-site photovoltaics and battery storage system, by contributing to the Pennsylvania state goal of a 26% reduction in greenhouse gases by 2025. We wanted to provide the university with a savings on their annual electric bill by having a functioning carport canopy solar system with battery storage in place by Q2 of 2023. And during grid outages, the university's critical load is supported with the battery storage system while simultaneously supporting load shifting and peak load shaving. The approach our team took to meet the objectives involved designing a multifunctional system that will increase solar usage and decrease grid usage. We wanted to ensure that the system meets the objectives of the team, the university, and the state. The system should protect the new science building's critical load during an outage, and the university and the investors should both be provided with favorable economics. I will now pass off to Kyle with the system design.
Thanks, Dalton. So given the two challenge areas, our team took a look at all of the open space available and all of the roofs available that we could use. And given the restricted amount of open space there was and the amount of obstructions that there could be for the small amount of roofs available within the challenge areas, we determined that the best course of action was to actually convert the two available north parking lots and south parking lot into carport systems. Shown are the north parking lot canopy system and the south parking lot system. Both systems implement the Halene 72M370 solar panels, which are 370 watt panels. These were chosen due to its positive commercial ratings and its high power rating and the number of cells. The reason we decided to finalize our project with the carport system was to avoid the need for rooftop inspections and to manage around potential obstacles like HVAC systems on the roof. Additionally, we have both of our systems running on 11 total ground-mounted SMA Sunny High Power Peak 3 150 inverters, which each are 150 kilowatt inverters. Shown is our north parking lot Irradiance model for the Aurora Solar program. The given irradiance range that we have for the north lot is between 1,460 and 770 kilowatt hours per meter squared per year. The average solar access that we could observe was about 98% with a tilt and orientation factor of 86% and an average TSRF of 85%. The north parking lot overall produces annually 1.18 million kilowatt hours with a system size of 985.3 kilowatts. The panel count for the north lot is 2,663, and this lot uses 5 out of the 11 SMA inverters. The south parking lot Irradiance model had an irradiance range of 1,460 to 250 kilowatt hours per meter squared per year, with an average solar access also of 98% and a tilt and orientation factor of 86%. The observed average TSRF was 84%, and the model's annual production was 1.27 million kilowatt hours. The system size in total was 1.1 megawatts with a panel count of 2916. And the inverter count here uses the remaining 6 out of the 11 inverters. For the energy production model, we have an aggregate of the two lots with the blue dots representing the south lot and the green lots representing the north lot. For the tail ends of the production, the simulation model accounts for the varying weather conditions for Pennsylvania. So we have lower production ends during the winter and fall of the year and a higher production count during the summers and spring of the year. We reach roughly about 800 kilowatt hours per an hour count with a average minimum around 300 to 400 given the daytime cycle.
Thank you, Kyle. For the battery storage system, the team investigated several possible solutions, with one system being the recommendation as it generates a positive net present value in terms of savings. The first solution the team decided to investigate was the Tesla Megapack, which was recommended to the team by several industry experts whom we consulted with. We determined it, however, to be financially unwise. Further details on that can be found in our submitted development plan. The battery system the team did settle on was the home grid batteries, which can be seen in figure 1 on the slide. These are 15 kilowatt, 38.4 kilowatt hour lithium iron phosphate batteries. By linking 10 of these batteries for an output of 150 kilowatts and 384 kilowatt hours, the system meets the 127 kilowatt critical load found in the new Science Center building on the campus. To minimize the length of connective wiring required, the location for the battery storage shed was chosen to be directly next to the new Science Center, as seen in the bottom right image on the slide. As Kyle mentioned, 11 Sunny high power peak 3 inverters seen in figure 2 were used. One sec, having an issue changing the slide, I think.
Oh, somebody else tried to request control. That wasn't your fault.
Oh, here we go. The software the team chose to use to analyze the battery system was the Reopt Lite web software, which is open source and developed by NREL. We used the load data provided by the university, as well as the simulated solar generation output by Aurora to simulate a 1-hour grid outage in Reopt Lite. We chose to place the simulated outage at the peak of the critical load, and the battery system was able to cover this for a little over an hour. At average load, the system would be able to cover an outage for roughly 3 hours. And if efforts were made to reduce the critical load, this outage period that we could cover could be extended. In our project submitted report, we do detail a outage action plan to reduce the load required. Besides these benefits, the home grid batteries include a 10-year warranty, and the system could also be used to reduce the peak load the university draws from the grid. If the university chooses to not pursue this route, the team also documented several recommendations in our written report for steps to be taken if no battery system is constructed. I'll now hand it off to Jong-soon to discuss the system risk factors.
Thank you, Mark. The diagram on the left shows the home grid stack series highlighting key details and components which led to the team's selection of this battery. The diagram on the right shows how the PV system would be interconnected with the grid. The solar panels would acquire the energy and transfer this energy to the Sunny central inverter. After doing so, the inverter would transfer this energy to both the batteries and the utility grid through the distribution lines put into place. Next slide, please. The system that the team created faced a few major risks, which were narrowed down to voltage and temperature regulation and equipment maintenance. To diminish the peak load based on the high thermal and voltage spots shown in the Cheyney University heat map, the team decided that the path drawn was the best path to connect the PV system to the main feeder line. Coupling this with the distribution lines that would be placed around these hotspots would diminish. The components such as batteries, inverters, and transformers are all components which would assist in voltage and temperature regulation, which is why general equipment maintenance is necessary.
I'll now discuss the system benefits. Our carport canopy system provides covered parking that provides shade to its users. We can also incorporate electrical vehicle charging with the carport canopy systems. The system utilizes preoccupied space that doesn't take away from nature, meaning that we don't have to use any fields or anything like that to have other uses for the university. It can improve the overall aesthetics of the university's parking lots by going through a repavement effort. We noticed that one of the parking lots wasn't the best pavement, and we figured that could go through this process. It allows for community events teaching about the benefits of solar. And we also determined that parking permit price can be increased due to the higher value of parking. This is some of the finances associated with our solar system. We use the Halene 72M370 solar panels. The total cost of all the panels came out to $1,813,000. And the current system on utility came out to a total annual cost of $211,178. And with the new system using a PPA price of 4 cents per kilowatt hour, we came up with a total annual cost of $190,996. The total project cost came out to $5,853,840. Next slide, please. The financial benefits, including the battery system, gave us a net present value savings of $508,157. And after the associated costs of the battery system, the net present value was determined to be $132,821. The battery system's payback period was 2.39 years. Over the total project, Cheyney would be saving about $20,000 annually, and the project IRR is 2.63%. The current cost of parking that we determined was $30 per year for a permit, and our suggested new price is $50 per year due to the benefits associated with it. And I will now pass off to Mark, who will discuss the construction plan.
Thank you, Dalton. Seen in this slide is the construction timeline the team constructed for the system. We decided to begin construction in Q1 of 2023 and to have an estimated finish date of the start of Q2. This flow diagram is a start to finish diagram. However, we did have some tasks overlap, such as the solar panel installation and the battery shed foundation pouring. This timeline is not a final plan, as after site grubbing and leveling, it may be determined that the parking lots require resurfacing, as Dalton mentioned. And as he also mentioned, the final savings due to the solar plus storage system, it's around $132,000 in savings. This includes the batteries, the inverters, the estimated battery maintenance, and the battery storage facility construction cost estimates. I'll now hand off to Connor to discuss the development risks and the community benefits.
Thank you, Mark. Our system has very little risk, with the part of the south lot only seeing 1% chance of flood annually. A zoning permit will be required along with certification from the Department of Conservation and the building code officer. We want to ensure the electricity will be transported to the battery safely, so an acceptable graded feeder line will be chosen. This system contributes to both the state renewable energy generation goal and the Delaware County 2035 action plan to establish an economically efficient and environmentally friendly community. Tours can also be held to teach campus visitors and aspiring students about the system, along with community events to promote the importance of renewable energy. Our system also requires the installation of carports, which gives the university a chance to repave the lot and improve the general aesthetics. Dalton will now summarize the system.
Thank you, Connor. Our team believes that our proposal should be selected because of the lack of risks associated with the proposal and the benefits that are provided to the university, its community, and the state of Pennsylvania. This proposal is a feasible option that allows Cheyney University to reduce their energy costs and consumption by expanding their on-site photovoltaics. Thank you.